Hey, what's up, Calc 2 crew, and welcome back to the Daily Problem Sets. Hey, today we're going to take a look at Chapter 11. We're going to start by talking about sequences, which here we just have a list of numbers in a particular order. And we want to know, is that list going to converge to something, to some finite value? Then it is convergent. If not, divergent. And again, you should have already taken a look at the lecture video for this content. We're just here to take a look at some extra examples. First, we'd like to find a formula for the general term a sub n for the following sequence. We then want the follow-up question, is the sequence convergent? And here we have the list of numbers: 1/9, 1/11, 1/13, 1/15, 1/17, so on and so forth. You probably get an idea as to what the rest of the list would look like. But writing it out in some general form, well, what we want to do is we want to try to find some way to reference what the first term is, what the second term is, and to sort of include that in our general form. So what I like to do is I would start by saying, okay, a sub 1, my first term is 1/9. I would then say a sub 2, my second term is 1/11. A sub 3, my third term is 1/13. And a sub 4, my fourth term, is 1/15, and so on and so forth. I'll just do these four to start. I can see that the number in the numerator is always 1, so that part shouldn't be so bad. And in the denominator, I can see that I have these odd numbers, and that is just sort of moving to that next odd number. But I want to try to find a way to reference the little subscripts that I have here, right? That is the first term, that is the second term, that is the third term, that is the fourth term. I want to try to include that in my generic formula. So if I go here to this 1/9, I can say, okay, well, that's 1 on top divided by, how can I think of 9? And here we want to use some sort of traditional definitions for even and odd numbers back from a discrete mathematics course. We'd say in general, the even numbers is 2 times k, where k is any integer, and then the odd numbers is just shifting this, that would be 2k plus 1. And this is how we would define even and odd numbers in general. Since I have odd numbers, I'm looking over here. It's likely not going to be identical to this definition, but I can use it to sort of help out. So here I could say, well, okay, for my odd number, for this 9, I could do 2 times 1, but then I'm going to have to add 7 to bring me up to 9. And this gives me a good place to start. I'll sort of put this one on the back burner and move on to the next one. Now with a sub 2, I want to try to reference this 2 here as my subscript. That's a 1/11, so I got 1 on top. For the 11, I could say, well, that's 2 times 2 plus 7. Right, 4 plus 7 gives me 11. For this 1/13, which is my third term, a sub 3, again, I want to try to reference this 3 here. I'd say, well, that's 1 on top, and then in the denominator, I could say, well, that's 2 times 3 plus 7. And then I have one more here to sort of consider. I want to reference this 4 for a sub 4. I have 1/15. I could say 1 over, in the bottom I could say 2 times 4 plus 7. And I want you to notice in particular, let me sort of showcase this or sort of highlight it, that I'm referencing this subscript in my formula. A sub 2, and there's where the 2 is. A sub 3, and there's where the 3 is. A sub 4, and there's where the 4 is. So then I can say, well, how does this look in general for any term a sub n? We could say, well, a sub n is equal to 1 divided by 2n plus 7. And as soon as I get this, I can check, because here we went first, second, third, fourth term. I didn't look at this fifth term, though. We'd say, well, what would a sub 5 be with this sort of closed form that I've generated? Well, I would plug this in for n. I would say 1/2 times 5 plus 7, or that's 1/10 plus 7 gives me 1/17. And that's what a sub 5 should be, 1/17. So it does check out, checks out perfectly. So here I have this general form for a sub n. I can say for any of these terms, it's just going to be 1/2n plus 7. Now I can use this to try to determine if the sequence is convergent. And to determine if the sequence is convergent or not, I want to take a look at the limit as n goes to infinity of a sub n. I want to know, what does that sort of long-term behavior look like? The limit as n goes to infinity of a sub n, and that would be the limit as n goes to infinity of 1 over 2n plus 7. And there's really not a lot of work to do here besides just talking about the limit. We would say, well, the numerator stays at 1, the denominator grows without bound, right? As n goes to infinity, 2n goes to infinity, 2n plus 7 goes to infinity. So it winds up looking like 1 divided by something that goes to infinity, which is going to give me 0. And since 0 is a finite number, this is convergent. We'd say the list would converge to 0 if I go very far out on that list. So this is convergent. Our sequence is convergent. Let's take a look at another example. Determine whether the sequence converges or diverges. Here we have a sub n is n cubed over 5n cubed plus 1. And again, I just want to set up the limit as n goes to infinity for this. So n cubed divided by 5n cubed plus 1. And there's a couple different tricks that we could use to try to figure out what this is. I think one of the nicest tricks to work with, or sort of my favorite trick, and we get a lot of good mileage out of this, would be divide each term by the highest power of n in the denominator. So divide each term by the highest power of n in the denominator. And how this would look sort of before we apply that actual trick is what I'm really saying is, okay, highest power of n in the denominator is n cubed. I want to divide everything by n cubed, but the reason why it sort of works is I'm using this clever form of the expression 1 as 1 over n cubed divided by 1 over n cubed. And then when I distribute this in, it's going to end up dividing each term from the original expression by n cubed. And let's see how that looks. So this is going to become the limit as n goes to infinity of, now in the top I'm going to have n cubed divided by n cubed. And then in the bottom, I'm going to have 5n cubed divided by n cubed. Plus, and I'm going to have 1 divided by n cubed. So everything gets divided by n cubed, essentially. And I can clean this up, say limit as n goes to infinity of, on the top, n cubed divided by n cubed gives me 1. In the bottom, 5n cubed divided by n cubed gives me 5. And then plus 1 over n cubed stays. And now I can talk about this limit as n goes to infinity. Really, n only appears in one of these terms left over. So we'd sort of go maybe to the side here, to the margin, and say, notice the limit as n goes to infinity of 1 over n cubed. And this is something where I have 1 on top and the denominator is going to infinity. We talked about that just a bit ago, that this is going to head to 0. So that's headed to 0. So then I can use that to tell me what the limit is. Now as n goes to infinity, I'm going to get 1 over 5 plus 0, which gives me 1/5. And 1/5 is some finite value, right? Just a regular looking number. So we'd say, well, this is convergent then. Here we have a convergent sequence. And then that list converges to 1/5. If I go far enough out on it, those numbers are going to look like they're getting closer and closer to 1/5. We'll see another example. Here I have a sub n is n cubed divided by 6n plus 3. So set up for that limit. Limit as n goes to infinity of n cubed over 6n plus 3. And here I'm going to divide each term by the highest power of n in the denominator again. Always want to look at the denominator for this. So I'd say the highest power of n in the denominator is just n to the first from the 6n term. So here we divide each term by n. Maybe you're looking at this and you already know what's going to happen with it. But if not, we'll take a look at it. So divide the numerator by n and everything in the denominator by n. So 6n over n plus, that's going to be 3 over n. And then I can reduce wherever I can. So limit as n goes to infinity of n cubed divided by n gives me n squared. Divided by, in the denominator I have 6. And then plus 3 over n stays as it is. And we can make, a comment here. We'd say, notice the limit as n goes to infinity of 3 over n gives me 0, right, like we've been saying so far. But on top, I want you to also notice that the limit as n goes to infinity of n squared is infinity. So if I were finding this limit, I'd say, well, okay, so the numerator is going to infinity, the denominator is going to 6 plus 0, which is just 6. So I have something headed to infinity divided by 6, which, that's not really, dividing by 6 isn't really going to do anything in this case. We're still headed to infinity. So this is headed to infinity as n goes to infinity. And infinity is not a finite number, of course. It's infinite. So we'd say, well, this is divergent, that we have a divergent sequence. Divergent. Let's see if this sequence converges or diverges. And this is just a different notation, right? We could say, a sub n equals, and we could express it. Or another common notation for sequences is just using this curly brace around what a sub n is. So this notation, we have our curly braces here. We have a sub n inside of it, Or like we saw in the very first example, we could have the curly braces, and then we could actually list out what a sub n is in terms of how the numbers look in the list. That's always a possibility. But so here we're given a sub n, and to find out if it's convergent or divergent, you guessed it, I want that limit. Give me the limit as n goes to infinity. Don't waste my time. And this looks very interesting. The limit as n goes to infinity of natural log of 6n divided by natural log of 12n. There are calculus tools that we can use, but we have to be careful with those. We'll talk about that in a bit. Otherwise, there's a lot of cool tricks that we can use from algebra to help us out. So what I would do, and I love logarithmic functions, I love log properties, I want to go on the record saying that, is I can go into the denominator, and I could say natural log of 12n, that's really natural log of 2 times 6n. Right? 2 times 6n is 12n, just writing it a bit differently. And then I can use a log property. I could say, okay, so I have ln of 6n on top. And then natural log of a product, I can write this as the sum of the logs of the factors. So I could say ln of 2 times 6n is ln of 2 plus ln of 6n. And it's not dissimilar from the trick that we've been using. Here we're going to say, sort of like divide by the highest power of n in the denominator, but really that means dividing by natural log of 6n is really the expression. And if I want to see it sort of in a bit more of a mathematical context, I could say, well, that means multiplying by 1 over ln of 6n divided by 1 over ln of 6n, and then sort of distributing that through. So we'll say, okay, well, so then how is this going to look? Right, the burning question. Limit as n goes to infinity. I have natural log of 6n. You get divided by natural log of 6n. All over in the bottom, I have natural log of 2. You get divided by natural log of 6n. I feel like I'm Oprah. And then plus, now I have natural log of 6n. Everybody, check under your seats. You're going to get divided by a natural log of 6n. Bam. Now I'm Emerald. On everybody. What is this going to give me? You got it. Limit as n goes to infinity of, on top I have 1. Same thing on top, same thing on bottom. In the denominator, I'm going to have ln of 2 divided by ln of 6n. Can't do much there, so I'm just going to rewrite it. And then plus 1. We'd say, okay, well now let's go ahead and talk about this a bit so that we can see where we're headed next with what we're doing. Let me get my little notice box. Notice the limit as n goes to infinity of natural log of 6n is infinity. Natural log, believe it or not, is an unbounded function. It's a slow growth, but it will go to infinity if left unchecked. And think about what that means then. So this term is really natural log of 2 divided by something headed to infinity. Natural log of 2 is just a number. just a number, just a constant. So I have a number divided by infinity, and we know what that's going to do. That's going to head to 0. So I could go here and I could put in my notice box, I could say limit as n goes to infinity of natural log of 2 divided by natural log of 6n, that this is actually 0. You'd say, well, let's apply this to our limit then. I have 1 divided by 0 plus 1, which gives me 1 over 1, which gives me 1. So here the sequence is headed to 1, and that means we're convergent. This is a finite number, so we have a convergent sequence. Very nice. Let's talk about things that alternate, right? If the sign switches, we could have something that maybe starts off as positive and then is negative and then et cetera, or vice versa. We have a very nice theorem to help us out. What does the theorem say? Let me tell you. It says if the limit as n goes to infinity of the absolute value of a sub n is 0, then we would conclude that the limit as n goes to infinity of a sub n is 0. So essentially what we're saying is if we have numbers that are getting smaller and smaller and heading to 0, the fact that it's alternating doesn't really take away from that. If I want to sort of think about it visually, I could say, well, what if I have, it could be either first positive and then negative, doesn't really matter, that's sort of arbitrary. I say, well, what if it's positive and then it's negative, and then it's positive again, but it's smaller in magnitude, and then negative again, but still smaller in magnitude, positive, negative, but getting smaller and smaller, and getting closer and closer to 0, you'd say, well, it's still headed to 0, right? It just does this sort of interesting thing where it's jumping around from positive to negative. So what we're suggesting is if I have something that does alternate its sign, like here I have a sub n is -1 to the power of n, divided by 5 times square root of n, so we'll throw it an absolute value and still look at the limit as n goes to infinity. So, okay, let's try it before we buy it. Limit as n goes to infinity of the absolute value of -1 to the n divided by 5 times square root of n. We'd say, well, -1 to the power of n, since n is just going to take on integer values, either starting at 1 or starting at 0, however it's sort of set up for the sequence, usually starting at 1. Then what we'd say is, well, it's either going to be a -1 or a positive 1. And if it's a positive 1, I can just get rid of the absolute value symbol. We notice here, I really wouldn't start it at 0 since this would be undefined. So starting it at n equals 1. So n takes on these values, but nothing in between, just stopping at these integers. We'd say, well, this is either going to be a positive 1, and I don't need the absolute value symbol, or it's a -1, in which case it's in the absolute value, which is a bad place for a -1. It's going to make it into a positive 1. So we'd say, okay then. So if I have the absolute value happening here, what's going to happen is this is just going to become 1 divided by 5 times square root of n. And if I want to take a look at what happens as n goes to infinity, I'd say, well, the numerator is headed to 1. It's stuck there, right? The denominator is going to infinity, right? Square root of something headed to infinity, it's going to infinity. But you think of it as the square root function heading to infinity, however you want to sort of visualize that. So then this is going to give me 0. Constant divided by something headed to infinity gives me 0. And what we can do is we could say, well, since the limit as n goes to infinity of the absolute value of a sub n gave me 0, then this means that the limit as n goes to infinity of classic recipe a sub n goes to 0. So that means the limit as n goes to infinity of -1 to the n divided by 5 times square root of n is 0, which means that we have a convergent sequence. So we can work with those absolute values if we need to. Absolutely, if we need to, we can work with absolute values to help out. Now, earlier we were talking about how we can use calculus to help us out. Hey, I'm here to talk. Let's talk about it. We have a very nice theorem. We're going to use it for this next example. We have if the limit as x goes to infinity of f of x is equal to some limit L, and if it just so happens that f evaluated at n gives us our representation for a sub n when n is an integer. Then the limit as n goes to infinity of a sub n is equal to L. And here we'd like to determine whether the following sequence converges or diverges. And here we have a sub n is n squared times e to the negative 3n. We start off like we would normally. Let's just set up for the limit. What's the worst that could happen? Now I would go here and I would rewrite this and say, well, let's think of this as the limit as n goes to infinity of n squared divided by e to the 3n. But this is a problem because the numerator goes to infinity, the denominator goes to infinity, so we have something that's a bit indeterminate, right? Sort of like an indeterminate form. And there's something that we automatically think about in calculus. We think we should use L'Hopital's rule, aka Bernoulli's rule, since Bernoulli came up with it, and L'Hopital just bought it off of him, which is kind of, you know, what a bummer. Hey, that's a story for another day, I think. If you want to get into some of that in the comment section below, let me know what you think about L'Hopital and what he did to Bernoulli. I don't know if it's very fair, but I don't think Bernoulli knew what he was doing either. I think it should be his name in all those textbooks. Anyways, don't just take it from dear old dad. Let me know your thoughts down below. But immediately, almost immediately, we're thinking, I know how to get out of the situation. I would like to use L'Hopital's rule. It would be a faux pas to use L'Hopital's rule with n, because n is not a continuous variable. It's a discrete variable. N only makes stops at the integer values, n equals 1, and then wait for it, n equals 2, and then wait for it, n equals 3. It's not continuous. It's stopping at the integer stops, and there's no information in between. If I want to take a derivative, if I want to work with differential calculus, and you better believe I want to, I need a continuous variable, which is where this theorem comes in. It says, okay, so let's think of this as a function of n. So I'll make some notes up here. My function of n is n squared divided by e to the 3n. And I want to model this, or model from this, a function of continuous variable x. And there's no great mystery where that function of x comes from. My function of x, let me know if you can guess what it is. I'm going to tell you what it is. It's x squared divided by e to the 3x. Can you guess where I got it from? I'm just swapping out discrete variable n for continuous variable x. So let's use this. Let's take a look at the limit of what this puppy is doing. Yeah. So limit as x goes to infinity of x squared divided by e to the 3x. This is where we're saying, let's bring him to the hospital. Let's use L'Hopital's rule. L'Hopital's rule. So we'll say, okay, that's the limit. Because it's indeterminate, I can use L'Hopital's rule. That's the one and only sort of precursor that I need to this, is that it is indeterminate. Let's take a look at the limit as x goes to infinity of, what is the derivative of the numerator? Derivative of x squared is 2x. What is the derivative of the denominator, e to the 3x? Well, that's going to be chain rule. I get e to the 3x, my outer derivative, times inner derivative 3. Hey, it's still indeterminate. Well, if it's still indeterminate, we don't give up. That means that we can use L'Hopital's rule again, since it is still indeterminate. So, bring them back to the hospital, L'Hopital's rule. Limit as x goes to infinity. The derivative on top, on the numerator, is going to give me 2. Then in the bottom, I need more chain rule. So we'd say, okay, 3, and then e to the 3. Well, 3 comes along, but let me wait on that. The derivative of e to the 3x is e to the 3x times another 3. So I get 3 times 3 from that 3 that's already there, so that's a 9. And I can find this limit. So say the limit as x goes to infinity of 2 over 9 e to the 3x gives me, numerator is a constant, denominator is headed to infinity, it's going to give me 0. But this came from, and we justified it, we were justified in using L'Hopital's rule since we had something that was indeterminate. I can now apply this theorem. I can say, well, I took a look at the limit as x goes to infinity of my function of x. It gave me a limiting value, capital L. And it just so happens that if I swap x back out with n, I get a sub n identically, then it follows that the limit as n goes to infinity of a sub n is also L. So I'd say, okay, so this means that the limit as n goes to infinity of my original, which was this n squared over e to the 3n, is equal to 0 as well. 0 is a finite number, so this is a convergent sequence. You might be thinking, oh, well, do I really have to do this? It wouldn't have just been faster to use L'Hopital's rule here. I'm saying, no, don't do it. We need a continuous variable. Don't use L'Hopital's rule with this discrete variable n. Don't take a derivative on n. That's not what we're here for. You know, you deserve better. The notation deserves better. Follow the rules. Don't wind up in calculus jail. I'm not going to bail you out. I might. Look it. I'm on your side, so I probably would. But I just don't want to be put in that position. I don't want to get that phone call late at night. I don't want to have to, try to find a way to, scrounge up the cash for you. So I'm here to help you now, telling you don't do it. Let's take a look at one more example, and then we're going to talk about series next. But sequences is what we're doing. Here we have the sequence r to the power of n is convergent if r is between -1 and 1. It's not allowed to be equal to -1, but it could be equal to +1, would be fine. And we'd say that it's divergent for all other values for r. And in fact, we would be able to actually say what happens when it is convergent. We'd say the limit as n goes to infinity of r to the n gives me 0 if r is between -1 and 1. So think of it like some proper fraction, either positive or negative. And if r is equal to 1, then that limit's going to give me 1 right on the nose. So, okay, so we'd say, well, let's take a look at using this to determine if the sequence that we have converges or diverges. We start off like we always do. The limit as n goes to infinity of 7 to the power of n plus 2 divided by 9 to the n. Now, I want this to look like r to the power of n. And I can see that the exponents on top and bottom aren't quite the same, but I can change this. I can deconstruct what I have a bit. I could say 7 to the n plus 2. Well, that's 7 to the n times 7 to the power of 2. And then in the bottom, I have 9 to the power of n. And from there, here I can take this, 7 squared, and I can, if I want to bring it out front of the limit notation, yeah, I can do that. It's just some coefficient. 7 squared, that's going to give me 49. Times the limit as n goes to infinity of 7 to the n divided by 9 to the n. And now that I have the same exponents, I can actually group that. I could say 49 times the limit as n goes to infinity of 7 divided by 9, all to the power of n. And now, so I do have this coefficient. I don't want to ignore it, but it's not what I'm looking at right now. I'm looking at my r to the n. I'd say, okay, r to the n. But what is r? R is 7/9. And this is between -1 and 1. It's less than 1 and it's positive. So we'd say, well, since r is between -1 and 1, the limit as n goes to infinity of r to the n gives me 0. So I'd be able to talk about this limit here. This is going to go to 0. So here I get 49 times 0, which gives me 0. It's finite then, so I have a convergent sequence. Convergent sequence. And this is going to come up again. This is some idea that we use to segue into talking about geometric series. And we'll talk about that next in the next section. We're talking about series, and there's a few theorems I want to start with. Theorem, test for divergence, then we're going to talk about geometric series. These first two things I want to talk about, I don't want you to misuse them. Be very careful with how you use them and how you interpret them. I don't want you to make the same mistakes that, I would. So be very careful. Don't be like me. Don't ever promise me. Promise me. This first theorem You're almost better off not even listening to me say it. Get out of here, Java. It says, if the series, the sum of a sub n is convergent, then the limit as n goes to infinity of a sub n is 0. It's not the other way around. So if you start with the limit as n goes to infinity of a sub n is 0, don't you dare make any conclusion from that information. It's not going to tell you anything. It has to go in this direction. And since we're going to be looking at determining whether or not a series is convergent with various series tests, I find it highly unlikely that you're going to really use this theorem too much. Don't misuse it, though, if you are going to use it. So we'd say if a series happens to be convergent, then from that piece of information, you can travel safely to say, well, then the limit of a sub n must be 0. However, if the limit of a sub n is 0, just quiet. Don't say anything. You don't know, because there's counterexamples. Take a look at counterexamples later on. I'm going to just give you a sort of a spoiler alert. A counterexample is the harmonic series. It's menacing. You don't like it, I don't like it. It really ruffles some feathers out there. But it's a counterexample, so don't say this the other way around. Don't you dare do it. Test for divergence. Test for divergence can be very difficult to get a good handle on because I see a lot of students sometimes using it to argue for convergence. Hey, doesn't make sense. You can only use the test for divergence to claim that something is divergent. Don't ever use it to say that something is convergent because you just can't use it that way. The test for divergence says if the limit as n goes to infinity of a sub n does not exist, or if the limit as n goes to infinity of a sub n does not equal 0, then the series is divergent. But I don't want you to take this to mean that, well, if the limit is 0 of a sub n, then it's convergent. Because it doesn't say anything about that. It never will. It'll never say that. I will never say that. So we can only use the test for divergence for divergence. So only use this for divergence. And don't make these things say things that they don't say. Don't make them infer things that they're not inferring, because it's not true. I'll tell you right now, it ain't true. But now, I'm done yelling at you for this moment. Let's talk about the geometric series. The sum from n equals 1 to infinity of a times r to the power of n minus 1, which we could write out longhand as a plus ar squared plus ar cubed plus ar to the fourth, keep going, is convergent if the absolute value of r is less than 1, so meaning r is between -1 and +1, and its sum is given by a divided by 1 minus r. However, if the absolute value of r is greater than or equal to 1, then the geometric series is divergent. There's two common ways to write the geometric series. You could write it many other ways. We usually see the sum from n equals 1 to infinity of a times r to the n minus 1, or we could say the sum from n equals 0 to infinity of a r to the n. And these are two common ways to write the geometric series. Notice, depending on what that starting index is, the exponent on r would have to be different to accommodate that. And that's important. Now, a few things I want to mention. First, we're talking about series in general, which means not just talking about a list of numbers, but now adding up the numbers on that list. We want to know, if I add those numbers up on the list, is the sum going to be convergent? With geometric series, we like to find what that sum is. We say if it is convergent, then the sum is going to be this a over 1 minus r. We don't do anything like this typically for other types of series. And we're going to find this later on in the course. We're going to say if it's geometric series, if it's a geometric series and it converges, I can tell you what it converges to. If it's a different kind of series, I'm likely only going to be able to tell you that it is convergent or divergent. But if it is convergent, I won't really be able to tell you what it converges to. It's just a lot more work. It's not something that we can nicely and easily do, and there's not a nice generic formula we can use outside of geometric series. And not for everything else, that's for sure. But let's take a look at some examples. Now let's start off with something to sort of bridge between sequence and series. We have let a sub n be equal to 5n divided by 7n plus 1, determine whether or not the sequence a sub n is convergent, and then we want to know, is the series for a sub n convergent? Now for the sequence, and we just talked about this in the previous section, I just want to look at the limit as n goes to infinity of my generating term, which is 5n divided by 7n plus 1. And we have that cool trick we like to do, divide by the highest power of n in the denominator, so divide by n to the first. So I get 5n over n divided by 7n over n plus 1 over n. And this is the limit as n goes to infinity of, here I'm going to have 5 divided by 7 plus 1 over n. And I can find this limit. Let's say, well, 1 over n goes to 0, so I get 5 over 7 plus 0. Gives me 5 over 7. And 5 over 7 is finite, so we would say that the sequence converges, convergent sequence. But now what I want to know is the series going to converge? So what about the sum from n equals 1 to infinity of this 5n over 7n plus 1? And here's where we can actually think about using that test for divergence. We would say, since our limit as n goes to infinity of a sub n does not equal 0, remember it was 5 over 7, does not equal 0, then the series is divergent. We can talk about this a bit more, but let's first write it down. The series is divergent since the limit as n goes to infinity of 5n over 7n plus 1 equals 5/7 does not equal 0. We would say by test for divergence. But let's think about this intuitively as well. We would say if my list, when I keep going out further and further on my list of numbers, if eventually the list is going to look like 5/7, 5/7, 5/7, 5/7, or getting close to those numbers, we'd say, well, what's going to happen if I start adding those together? Now I'm adding up everything on this list, these positive terms, and eventually I'm going to get to 5/7 plus 5/7 plus 5/7 plus 5/7, so on and so forth. That's not going to stop. It's not going to converge. We're going to say, well, you just keep adding 5/7. If I asked you, let's be honest here, if I said, I want you to keep adding 5/7 over and over and over again forever, don't you ever stop, let me know what you get for an answer, you'd think I was crazy. You'd say, I'm not playing this game. You're not going to fool me again, old beardy. I don't want to do this. It's not going to work. I'd say, well, yeah, you're right, because it's divergent. You're not going to get an answer. You're not. Not going to happen. Well, let's talk about some geometric series. Here I have a geometric series. I'm told it's a geometric series. I want to determine if it's convergent or divergent. I have 10 minus 6 plus 3.6 minus 2.16 plus so on and so forth. It might seem difficult, and it kind of is because I'm not given some closed form for the geometric series, but there's a nice trick I could use here. I could say, well, if I want to think about this as the sum from, could be n equals 0 to infinity or n equals 1 to infinity. Let's just do n equals 0 to infinity of ar to the n. This would look like, written out longhand, a plus ar squared plus ar cubed plus so on and so forth. And if I know that this is a geometric series, which I'm told that it is, that means this very first term should be a. So a should be 10. And that second term, the second term should be ar. So ar should be negative 6. And I know what a is. So I'd say, well, r is negative 6 divided by a, but a is 10. Negative 6 divided by 10. You should reduce. Negative 3 over 5 is r. And like what we said about the geometric series at the beginning, we could say since the absolute value of r is less than 1, right? Negative 3/5 is between negative 1 and 1. That means we have a geometric series that converges. I have a convergent geometric series. R is between -1 and 1. But a follow-up question is, well, what does it converge to? We'd say it converges to a over 1 minus r, but I know what these pieces are, so I want to throw it in there. A is 10, divided by 1 minus r is -3/5. And you know we shouldn't leave our answer like this, so let's keep going with it. We'll say, well, that's equal to 10 divided by 1 plus 3/5. Little com denom action, never hurt nobody. 1 is 5/5 plus 3/5. So that's 10 divided by 8/5. You know we shouldn't divide by a fraction, multiply by the reciprocal instead. So 10 times 5 divided by 8. I can reduce 10 over 8. I can reduce by 2. So here 2 goes into 10 5 times and into 8 4 times. So and this is going to give me, we'll say it converges to 25 over 4. So with a geometric series, not only can I tell you if it's convergent or divergent, but if it is convergent, I can find what it converges to, what that sum is. If I were to keep adding up the numbers on this list in this fashion, it would eventually slow and would be headed towards the number 25/4, which is really cool that we can do that with a geometric series. Let's take a look at another example. Determine if the geometric series is convergent or divergent. Here I have the sum from n equals 1 to infinity of 7 to the n divided by -3 to the n minus 1. Very careful. We have to make sure that we know what we're working with here. I have the sum from n equals 1 to infinity, so that means it should be ar to the n minus 1 power. And I can see that I don't have the correct exponents on this, so I have the sum from n equals 1 to infinity of 7 to the n divided by -3 to the n minus 1. But this is what I need. I need this type of form here. It looks like the denominator got the memo. It looks like the numerator didn't. But I can fix this. I can fix it. In the numerator, I can bring a 7 out and say, well, 7 to the n is 7 times 7 to the n minus 1. Sort of breaking off one piece of the base there. And now I can write this as the sum from n equals 1 to infinity of, I have 7, the 7 that I broke off. Since the rest of this has the same exponent, n minus 1, I can collect it as -7 over 3 all to the power of n minus 1. You could leave the minus sign in the denominator. I don't think, I just brought it to the top. You can put it in front of the fraction, but it's -7/3 to the power of n minus 1. Which means here I can see a is 7 and r is -7/3. We're really just looking at r right away to determine if it's going to converge or diverge. This is too big, right? We'd say since the absolute value of r is not less than 1, right? It's too far out in the negative direction. It's not between -1 and 1. -7/3 is too far out in that other direction. We'd say the geometric series is divergent. And since it's divergent, I wouldn't be able to tell you what the sum is because it's divergent as a series. We'll take a look at a couple more examples. I want to determine if the geometric series is convergent or divergent. Here I have the sum from n equals 1 to infinity of e to the n divided by 5 to the n minus 1 power. Again, as soon as you see it, that starting index means we want a r to the n minus 1. That other common form, let me just refresh your memory, n equals 0 to infinity of ar to the n. We don't have that. This is what we have. I want it to look just like this. And I have the sum from n equals 1 to infinity of e to the n divided by 5 to the n minus 1. I want this to have the same exponent, n minus 1. So we got to use that trick again. Let's bring an e out. So e to the n is the same as e to the first times e to the n minus 1. And now I could say, well, this is the sum from n equals 1 to infinity of e times, and I can group these terms that have the same exponent, and I could say, well, that's e divided by 5 all to the power of n minus 1. And now I can see what I have. I have a as e, and I have r is e over 5. And I want to know, is r between -1 and +1? It is. Remember, e is about 2.718, so on and so forth. Do this kind of hand move when you're explaining that stuff. Helps. E is certainly smaller than 5. So this is a proper fraction. So we'd say since r is between -1 and 1, we have that the geometric series is convergent and the series converges to, since it is a convergent geometric series, I can tell you what it converges to. It's going to converge to a over 1 minus r. But I know what these pieces are, so I should be solving this, which is going to be e over 1 minus e over 5. And well, here, let me rewrite it. But I don't want to leave it like this. It's a complex fraction. You could get a common denominator and work from there. I think that's a normal move to make. You could also work with, even faster, the LCD method. I'm going to multiply by 5 over 5, which is just the number 1. And this is going to give me, on top, e times 5 is 5e. Distribute in the bottom, 5 times 1 is 5, minus 5 times e over 5 is just going to give me e. And that looks really nice. So not only is the geometric series convergent, I can tell you what it converges to. Converges to 5e divided by 5 minus e. Take a look at one more example here, and then, hey, we're going to yeet on out of here. I want to determine if the series is convergent or divergent. I have the sum from n equals 1 to infinity of 1 plus 6 to the n, all divided by 7 to the n. There's a bit of a trick with this one, is that I'm not really given kind of one series to analyze, but I'm really given 2 for the price of 1. So what a bargain. But what I want to do is I want to break this up. I want to say sum from n equals 1 to infinity of, I can split this up as 1 over 7 to the n plus 6 to the n over 7 to the n. And what I can do is I can write these as 2 separate series. I could say sum from n equals 1 to infinity of 1 over 7 to the n plus the sum from n equals 1 to infinity of 6 to the n over 7 to the n. Now there's a really cool sort of move I can make here. I could say since my numerator is 1, I could write it as 1 to the power of n for free. It isn't really advantageous to do that necessarily, except for when I'm trying to do what I'm doing right now. Because I'd say, well, if it's 1 to the n, 1 to the first power, 1 squared, 1 cubed, 1 to the fourth, 1 to the fifth, 1 to the sixth, 1 to the seventh, they're all 1. They're all 1. But in this case, I use that as an advantage and say, well, I can write it this way, and it's not incorrect. It's still fine. And this allows me to group what I have. So I'd say here I have the sum from n equals 1 to infinity of, I could say 1 over 7 all to the power of n, plus the sum from n equals 1 to infinity, and I can group these together, 6 over 7 all to the power of n. Let me sort of do this sort of linearly on my way down. I'd say, well, this isn't quite what I want. Remember, if it's starting at n equals 1, I want ar to the power of n minus 1. So I have to clean this up, but I can clean it up like I've been doing. I could say sum from n equals 1 to infinity of 1/7 times 1/7 to the n minus 1, plus the sum from n equals 1 to infinity of 6 over 7 times 6 over 7 to the n minus 1. And I can look at these separately. I could say for the first geometric series, a is 1/7, r is 1/7, and that since r is between -1 and 1, that this is convergent. For this other one here, I could say a is 6/7, r is 6/7, and same idea is that since r is between -1 and 1, I have a convergent geometric series. So both of these are convergent. Since both of them converge, the sum of them converge. I want to point out, though, that if one of them was divergent or both of them were divergent, then it would be divergent overall. But since this first one here is going to sum to some finite number, since it is convergent, and the second one is also going to sum to some finite number because it's convergent, that adding them together maintains that we're convergent, doesn't disrupt it, keeps that convergence, right? And if I want to know then what this is going to converge to, I should be able to find it. So I can comment first. I can say, well, then this means it's convergent overall. So we'd say the sum is convergent overall, since both of these are convergent. And what does it converge to in total? Well, the first one is a over 1 minus r, which is going to be 1/7 over 1 minus 1/7. And I'll come back, I'll fix this up. But the other one is going to converge to a over 1 minus r as well, which is 6/7 over 1 minus 6/7. And we'll say, okay, let's see if we can make any progress with these. Here for this first one, let me use that LCD method. Let me do 7/7. And I'll do the same over here, 7/7. Try to clean them up. And what are we going to get? Here for this first one, if I multiply out, I'm going to get 7 times 1/7 is 1 over, here I get 7 minus 1. I'll come back to this. If I move over to this other one, I'll say, well, here, if I multiply the 7 in, I get 6 over 7 minus 6. So here, this first one is going to give me 1/6. This next one here is going to give me 6/1, which I'm going to get a common denominator because you probably know what I'm going to do with these two as separate answers. If I multiply this by 6/6, gives me 36/6. I know what they converge to separately, but if I want to know what the whole situation converges to, I want to add these together. So I want 1/6 plus 36/6 gives me 37 divided by 6 is what the series converges to. And what was it? That was 1 plus 6 to the n all over 7 to the n. So I know that this is what this converges to. Kind of in the way, but I'll move my little face. Hey, where am I going? What have you done to me? So this, believe it or not, this series here, it's really the sum of two convergent geometric series popped into one. It is convergent overall, and the sum, if you sit there, you add everything up, it's going to want to go to 37 divided by 6. Hey, I hope you've had a great time. I've had an awesome time. I love talking about this stuff. Let me know what I can do to help. I hope you're doing great on your calculus journey. If you're part of the Calc 2 crew, let me know with some hashtags down below. Let me know what you think about this material. Make sure that you're keeping up with the lecture videos. Make sure you're doing the homework online. If you have any questions, you know where to find me. We're going to be back with more content soon. Remember, no matter what, to always keep learning, keep dreaming, follow your heart. We're going to be back with more of the calculus, more of the cats. I'm here to help you. Let's keep this going. Let's do more of this. This has been good. Had a good time. I hope you had a good time too. I hope the rest of your day goes great. I'll see you next time. Until then, take care. All right, I'll see you.